Introduction to Monotonicity. To begin, here are some basics of reading a graph. Just like a book, we read a graph from left to right. We are interested in describing what is happening to the function values f of x, or the y values, but we provide our answers from along the x-axis. So we use intervals from along the x-axis to typically describe what's happening to the function values on that particular interval of x values. And finally, the zeros of a function, or really more specifically the real zeros of a function, are its x-intercepts. So finding the zero, setting a function equal to 0, and getting out real numbers, what you have found are its x-intercepts. So now I want to review, where is a function positive or negative? So a function f of x is positive when its y values are above the x-axis. A function f of x is negative when its y values are below the x-axis. So again, our answers should be the x intervals where the function is positive or negative. So it's important to note that 0 is not a positive or negative number. So in these next two examples, I want to find where each of these functions are positive or negative, and we want to give our answers in interval notation. So let's say this is the function f of x, and I want to know where is f of x positive. And I'm going to write that in a different way right now. This is like asking, where is f of x greater than 0? So I'm looking for where the function is above the x-axis. So I'm going to highlight that particular region. That happens right here. This is where the function is above the x-axis, so on top of the x-axis. So this purple portion is where the y values are above the x-axis. Now I want to give my answer from the x-axis. So from -1 to 1, that is the x interval where my y values are above the x-axis. So because I want to be strictly above the x-axis, not equal to the x-axis, I have to use open parentheses. So now if I want to find where f of x is negative, that's like asking, where is f of x less than 0? So that's going to happen. Let's do that in a different color. So this graph is below the x-axis down here, and I'm going to assume this graph goes down forever. So I'm going to go ahead and include these arrows. Let's say that was part of the graph. So now I want to read this on x intervals where this green portion is occurring. This green portion is negative below the x-axis. So on what x intervals does this occur? So from -infinity to -1 is where my function is below the x-axis over here on this side. So because this arrow goes down forever, it's technically also going left forever. So all the way from -infinity to -1 is my graph negative or below the x-axis, and again I want to have open parentheses around -1 because I want to know when I'm strictly below the x-axis, not equal to it. And then from 1 to infinity, because this graph goes down forever, but it also is opening wide and going right forever. So from -infinity to -1, and from -1 to infinity. So this U is a symbol that means union, or really translates to and. So there's two different intervals and they're separated by this union, meaning and, as in both of these are my solution. So now let's try to do that same thing with this function over here. So let's say this is my function f of x. I want to know where f of x is positive. So I'm going to stick to this notation, where is f of x greater than 0? So this graph looks like it's almost always above the x-axis. So again, I'm going to, let's say they did have arrows pointing up, so these graphs go on and on forever. So this graph is above the x-axis from -infinity, way off to the left, all the way until 2. But at 2, my function equals 0, so it's not greater than 0. So from -infinity to 2, open, my function is above the x-axis, and from 2 all the way to infinity. So right here at 2, there is an x-intercept. So this is where my function equals 0. And remember, 0 is not positive or negative. So that means I cannot include 2 as part of my answer. So this graph is above the x-axis from negative infinity to 2 and from 2 to infinity. So in other words, this function is negative or less than 0 nowhere. So there's no x value where the y values are below the x-axis. So nowhere in interval notation can be written with this like a 0 with a sideways line through it. So this means the empty set. So this means nowhere. There's nowhere the function is below the x-axis or negative. Now we can look at monotonicity. We say that a function f of x is monotonic on the open interval from a to b if it is either increasing or decreasing on the open interval from a to b. In general, monotonicity is the study of where f of x is either increasing or decreasing. So now let's take a look at the formal and informal definitions of what it means to be increasing or decreasing. A function f of x is increasing on the x interval from a to b if f of x1 is less than f of x2 for all x1 and x2 in the interval from a to b, the symbol means in, such that x1 was less than x2. So this is a very technical way of saying things, but what's happening is if I have some value x1 that's less than x2, or really to the left, because smaller values are on the left on the number line on the x-axis. So if I have some x value that's less than some other x value, and I substitute each of those into the function f of x, if the y value of x1 is less than the y value at x2, then this function is increasing. So I want my y values to go from smaller to bigger as I move from left to right. So an informal way of saying this is that a function is increasing when from left to right, it looks like on the graph we're walking up a hill because we want those y values to be getting bigger. So here's kind of a cute little picture I found on coolmath.com. So it's got this little ant here, and if we were trying to determine where this function is increasing, it's where this little ant, it's on the x values where this ant is walking up a hill. So that's going to happen on an interval from negative infinity to negative 3. So this function is increasing from negative infinity to negative 3. And then it starts increasing again from an x value of 1 to an x value of 4. So and, meaning the union symbol, 1 to 4. So on these x values, so since this goes down forever, as I look from left to right, he would be walking up a hill from negative infinity to negative 3, and then from 1 to 4. Whereas on the other hand, a function is decreasing on an interval if now f of x1 is greater than f of x2. So as I move from left to right, the values start out greater and then get smaller. So the y values start going down. So informally, a function is decreasing when from left to right, we're going down a hill, or the y values are getting smaller. So now here's a little ant from negative 3 to 1. This little ant is like it's walking or sliding, in this case, down a hill. So we have a decreasing interval from negative 3 to 1. So this little note on the bottom says, intervals of increasing and decreasing are by definition always open intervals. So we don't need to think about the endpoints. By definition, when we talk about monotonicity, we're talking about open intervals of increasing and decreasing. So we don't have to ever worry about the endpoints. Now, it varies by textbook, but we will, and the AP test defines them to always be open intervals, so there's no need to think about those endpoints. And then finally, what's not mentioned on here, because we're strictly talking about intervals of increasing or decreasing, past 4, you'll notice that this function stays the same. The y values aren't getting bigger or smaller. So from 4 to infinity, this function is constant. But again, we're trying to study where the function is increasing or decreasing. Alright, so here are some examples. Find the intervals of increasing or decreasing on the graph of f of x below. So each of these are original functions f of x, and we want to find intervals of increasing and decreasing on each one. So before I even write the intervals, I want to, on the graph, label which portion is increasing and which portion is decreasing. So over here, off to the right, as I move from left to right, starting at 2 all the way to infinity, it's like I'd be walking up a hill. So it's pretty easy to tell when it's a linear function like this. So this is a piecewise linear function. So right here, my graph is increasing. So as I move from left to right, it's like I'm walking up a hill. And then over here on the left side, so from negative infinity to 2 on the x-axis, all of my y values are getting smaller. It's like I'm walking down a hill. So I just wanted to start out by labeling each portion of the graph because I want it to be really clear what it means to be increasing and decreasing. So my graph is now increasing on the interval. So now let's think about the x intervals where this is happening. We are increasing from the x value 2, and since this goes to the right forever, to positive infinity. So I'm increasing from 2 to infinity. And again, I don't need to think about the endpoints. They're always open intervals. And I'm decreasing all the way from negative infinity to positive 2. So now let's take a look at this example. If I look from left to right, over here, I start out an increasing function. So now here, I'm walking up a hill if I were walking from left to right, and then over here, I start decreasing. So that change happens right here at this absolute maximum, or this maximum value, but that is an x value of 0. So my graph is increasing from negative infinity to 0 on the x-axis, and then it starts decreasing past 0 all the way to positive infinity. So decreasing from 0 to infinity. Alright, so up until now, we really haven't done much calculus. So the idea of increasing or decreasing, or the formal notion of monotonicity, is really a pre-calculus concept. But given a function to find intervals of increasing and decreasing, we can now start to involve calculus in this situation. So this theorem tells us that if we have a differentiable function f of x on the open interval from a to b, if the derivative is always greater than 0 for all x in the interval from a to b, so if the derivative is greater than 0, meaning the derivative is positive, then the original function f of x is increasing on a to b. So there's a distinct difference between being positive and increasing. So if the derivative is positive on a particular interval, then the original function is increasing on the interval from a to b. And then if the derivative is negative over the interval from a to b, then the original function must be decreasing on the interval from a to b. So it's really important to know that this only works in this direction. So if the derivative is positive, the original function is increasing. If the derivative is negative, the original function is decreasing. But this doesn't mean that if the original function is increasing, then the derivative must have been positive on the interval. So it doesn't work this way. I have to know that the derivative is positive to know the function's increasing. But the function might be increasing and the derivative may not be positive. So here's a counterexample that shows why it doesn't work in the reverse direction. So this is the function x cubed here, and this function is increasing everywhere. So as I move from left to right, so if I start way over here on the left, my y values as I draw this graph just keep going up and up and up and up. So my y values are getting bigger and bigger from negative infinity to infinity. So this function is increasing from negative infinity to infinity. But at 0, if I were to draw a tangent line, my derivative at 0 would be 0. I have a horizontal tangent line at 0 on the graph of x cubed. So f prime of 0 equals 0. So if I attempted to say, well, because this graph is increasing, so because f is increasing on negative infinity to infinity, then that must mean that f prime is positive or greater than 0 everywhere. That would be false because f prime of 0 equals 0. f prime of 0 is not greater than 0. So this one value at 0 contradicts this statement. So f is increasing everywhere, but f prime is greater than 0 only from negative infinity to 0 and from 0 to infinity. So I cannot include 0 in this right part of the statement. So that means that it doesn't work in reverse. So derivative positive, function's increasing. But if a function's increasing, we cannot say that the derivative is positive. It only works in the forward direction. Okay, so now our goal is going to be to determine where a function is increasing or decreasing, and we're going to do this using a sign chart. So the steps to follow involve first finding all x values where f prime of x is 0 or undefined. And then we take those x values and we plot them on a number line and break up the number line into open intervals. And then we're going to choose a test value from each interval to substitute into f prime of x to determine if f prime of x is positive or negative on that interval. Because on the intervals where f prime of x is positive, then we know that f of x must be increasing. And on the intervals where the derivative is negative, then f of x is decreasing. So in general, what we're trying to do is find where the derivative is positive or negative. So the other option would be graphing f prime of x and determining the x intervals where f prime of x is above or below the x-axis. Alright, in these next few examples, we want to find monotonic intervals analytically or graphically given f of x. So ultimately, what the goal is going to be is to try to find where the derivative is positive or negative. So let me write that in the corner. Our ultimate goal is to figure out where is f prime of x positive and where is f prime of x negative. Now, in certain instances, it's going to be useful to create a sign chart. But if we don't have to, then we shouldn't. So let's keep this goal in mind. So find the intervals on which f of x equals x squared minus 2x minus 3 is increasing or decreasing. So again, we're trying to figure out where the derivative is positive, because that's where the original function is increasing, and where the derivative is negative, that's where the original function is decreasing. So f prime of x, in this case, the derivative, is the function 2x minus 2 by the power rule. So this is a nice derivative. This is a linear function. So again, what the ultimate goal is to try to figure out, well, where is f prime of x greater than 0, and where is f prime of x less than 0? Since f prime of x is this nice linear function, to solve this inequality analytically and directly without a sign chart would be a rather simple process. I could add the 2 to the other side and then divide both sides by 2. So I would get the interval when x is greater than 1. So the function, the derivative function, is positive when x is greater than 1, or in interval notation, from 1 to infinity. So if f prime is greater than 0 from 1 to infinity, that means that f is increasing on the interval from 1 to infinity. So for increasing intervals, f prime of x is greater than 0 on 1 to infinity, so f of x is increasing on 1 to infinity. So we've answered the increasing portion. So now for decreasing, I take the same derivative, 2x minus 2, and determine where the derivative is less than 0. So I'm going to add 2 to the other side. 2x is less than 2. Divide both sides by 2. I get x is less than 1 this time, which in interval notation is negative infinity to 1. So the derivative is negative from negative infinity to 1. So I can conclude that because f prime of x is less than 0 on negative infinity to 1, then f prime of x, the original function, is decreasing on the interval from negative infinity to 1. So this is my answer, and I really want to get in the habit of including my explanation, and that is in reference to the theorem that we previously looked at, that if the derivative is positive, the original function is increasing. If the derivative is negative, the original function is decreasing. Alright, next example. Find the intervals on which this cubic function here is increasing or decreasing. So again, our goal is to determine where the derivative is positive or negative to help us answer this question. So the derivative, in this case, by the power rule, if I bring the 3 to the front, the 3 and the 1/3 cancel, so I end up with negative x squared. Bringing the 2 to the front, the 2 and the 1/2 cancel, I get plus x, and then plus 6. So here's my derivative function. I want to know when this function is positive and when this function is negative. So ultimately, here's what I'm looking for. Where is negative x squared plus x plus 6 greater than 0? And when is negative x squared plus x plus 6 less than 0? So we can take one of two approaches here. We can do this graphically, or we can do this analytically. Now, since this is a quadratic function, I would say that it isn't a bad function to do graphically. So what we could do is find the x-intercepts of this function and then graph it. So I'm going to go ahead and have to factor this equation here. So I'm going to go ahead and pull out a negative to make the leading coefficient a positive 1. So this is the same as x squared minus x minus 6 if I pull out a negative. And then I can factor, and I would get x minus 3, x plus 2. So my x-intercepts, if I set this equal to 0, are going to be 3 and negative 2. So if I were to do a sketch of this graph, I have negative 2 as an x-intercept, I have 3 as an x-intercept, and because the leading coefficient is negative, because there's a negative in the front, and it's a quadratic, this is a parabola that opens downward. So I know it goes through these 2 points. I know it has a y-intercept of 6, although that value is not very important. What's important is that this parabola opens downward because of the negative leading coefficient. So if I know that this is the graph of f prime of x, I want to know when f prime of x, when the derivative, right, that's this portion here, this is f prime of x, when is f prime of x positive? And then this again is f prime of x, so I'm interested in when is f prime of x negative? So if I read this graph, where is this derivative graph positive? I'm looking at the x values on which this graph is above the x-axis. So that occurs from negative 2 to 3. So f prime of x is positive from negative 2 to 3, and f prime of x is negative or below the x-axis from negative infinity to negative 2, and from 3 to infinity. So these are my answers for where the function, the original function f of x, is increasing, and then where the original function is decreasing. So my summary is that since f prime of x is greater than 0 on negative 2 to 3, f is increasing on negative 2 to 3. And then similarly, since f prime of x is less than 0 on these two intervals, negative infinity to negative 2 and 3 to infinity, that means that f is decreasing on negative infinity to negative 2 and 3 to infinity. So I want to summarize my results, and we did this problem graphically. But we still had to find the derivative, and we needed to be able to graph the derivative accurately to determine where the derivative is positive or above the x-axis and where the derivative is negative or below the x-axis. Alright, we reached an example where I'm going to use a sign chart. So find the intervals on which f of x equals x to the 5th minus 5x cubed is increasing or decreasing. So again, we want to know where the derivative is positive or negative, but this derivative is about to be 5x to the 4th minus 15x squared. So this is not something that you would be able to graph by hand. At least it's not something that I would expect you to be able to graph by hand, although it can be done. So instead, what we're going to do is follow that set of steps for applying a sign chart to this problem. So what we want to do is we want to figure out where the derivative equals 0 or is undefined. So I want to set 5x to the 4th minus 15x squared equal to 0. So to make it a little nicer, let's pull out a 5x squared. And what's left over is an x squared from the first term, and just a minus 3 from the second term. So we're setting each of these pieces equal to 0. So this is the zero product property. I'm going to set 5x squared equal to 0 and x squared minus 3 equal to 0. So if I divide by 5, take the square root of both sides, this left equation is going to leave me with just x equals 0. This right one, I'm going to get x squared equals 3, so x equals plus or minus the square root of 3. So there are 3 places where the derivative is 0. So what we just found was 3 x-intercepts on the graph of the derivative. But the problem is we don't know exactly what's happening on each of those intervals. So let's imagine that this number line that I'm about to draw is the x-axis. So we're drawing a number line and we're plotting the zeros on the number line. So 0 is one of my zeros, negative radical 3, and radical 3. And this number line spans from negative infinity to infinity. And to remind ourselves, this is a number line regarding f prime of x. So what we're trying to do is we're trying to figure out if this is a number line regarding f prime of x, and you don't have to write this next part down, if we could, we would like to ideally draw the graph of f prime of x to figure out, well, between negative infinity and negative radical 3, is the graph of f prime of x, is it up here? Is it above the x-axis? Because if it is, then the derivative is positive, so the original function is increasing. And then maybe between negative radical 3 and 0, maybe I go below the x-axis on the graph of the derivative, meaning the derivative is negative, so the original function is decreasing. So that's what I'm trying to figure out. What's going on over all of these intervals? So let's create all of the possible intervals. So my intervals are going to go from negative infinity to negative radical 3, from negative radical 3 to 0, from 0 to rad 3, and from rad 3 to infinity. So these are all my possible intervals where the derivative is either positive or negative. So now I have to pick test points in each of these intervals, and I want to think about the nicest possible number I can choose in each interval. So negative radical 3, I know that's a number that's less than negative 2 because radical 3 is less than radical 4. So a test point is the next thing I need to choose, so I'm going to write that as TP. So my test point is going to be, in this interval, negative 2. Now between negative radical 3 and 0, I'm going to choose the test point negative 1. Between 0 and rad 3, 1, and between rad 3 and infinity, 2. So now what I need to do is plug these test points into the derivative function. So here's where it's important to understand the concept, because in the previous section we were plugging the test or the critical points and the endpoints into the original function. We were trying to find the absolute max and min. Here, we're trying to determine whether these intervals on the graph of the derivative are positive or negative, because that will tell us whether the original function is increasing or decreasing. So I need to plug the test points into the derivative function. So I need to plug the test points in here. Or the simplified version, I can plug them in here as well. This is the same function, just factored out 5x squared. So what I'm interested in, this next line of my little sign chart, is going to say the sine, this is what I'm interested in, the sine of f prime of x. So my test points are chosen. When I substitute the test point into the derivative, what's the sign that comes out, positive or negative? So if I plug in negative 2, so I need to think about plugging negative 2. I'm going to choose this, this one to plug them into. So if I plug in negative 2, right here, I'm going to get a positive value because negative 2 squared is positive. And then if I plug negative 2 into this part, negative 2 squared is positive 4, and 4 minus 3 is positive. So I'm going to have a positive times a positive. So the sign of f prime of x at negative 2 is positive. Now we try negative 1. So if I substitute negative 1 in right here, 5 times negative 1 squared is positive, so this part is positive. Negative 1 squared is positive 1, and positive 1 minus 3 is negative 2. So a negative times a positive is going to give me a negative. So on this interval from negative rad 3 to 0, the derivative is negative. Now we try 1. So if I plug in a 1, 1 squared is positive, so this is positive. 1 squared is 1 minus 3. I'm going to get that negative 2 again, so I'll get a negative. And then finally 2. So 2 squared is positive 4, so this quantity will be positive. And then 2 squared is 4 minus 3 is positive. So two positives multiplied together are positive. So hopefully you don't actually need to plug in the number and find the actual value to determine the sign. It's just a matter of determining whether the result will be positive or negative. We don't care about the specific value. So now that we know what is happening to the derivative over each of these intervals, we can determine whether f is increasing or decreasing. So because f prime is positive on this interval f must be increasing. And on this interval, f must be decreasing. On this interval, because the derivative is negative, f must be decreasing. And because the derivative is positive, f must be increasing. So our conclusion is, since f prime is greater than 0, so f prime is positive on, let's highlight those intervals. We had positive right here to correspond to this one, and positive right here to correspond to this one. So since f prime is positive on negative infinity to negative rad 3 and rad 3 to infinity, f is increasing on those intervals. And then similarly, because f prime is less than 0 on these two middle intervals, so from negative rad 3 to 0 and 0 to rad 3, f is decreasing on those intervals. And that's it. So this type of problem, ideally, if we can graph the derivative to try to analyze where it's above or below the x-axis, that would be ideal. Or if we end up the derivative is just linear, then that's an easy thing to set greater than or equal to 0. So what we had to do was think about what happened to the derivative over each of my potential intervals. And then if the derivative was positive, the original function was increasing. If the derivative is negative, the original function is decreasing. Alright, so now we're going to find monotonic intervals graphically given f prime of x. So now we're starting off the problem giving you the graph of the derivative function. So in this example, we have the graph of f prime of x. Find the intervals where f of x, the original function, is increasing or decreasing. So remember that the original function is increasing where the derivative is positive. So what we're being asked to find is, where is f prime of x greater than 0 and where is f prime of x less than 0. So this is the graph, just to remind us, of f prime of x. This is the graph of the derivative, and we're assuming these arrows go on forever. So what we're looking for is, where is this derivative graph positive? Where is this graph above the x-axis? So this is happening from negative infinity to negative 1. So on that interval, from negative infinity to negative 1, this graph is above the x-axis. And from 3 to infinity, this graph is also above the x-axis. So negative infinity to negative 1 and 3 to infinity is where the derivative is greater than 0. So what we can say is that since f prime of x is greater than 0 on negative infinity to negative 1 and 3 to infinity, that must mean that f is increasing on those same intervals, negative infinity to negative 1 and 3 to infinity. So the reasoning is required. We have to explain that we really understand what's happening. So if we also want to find where f, the original function, is decreasing, we need to find where f prime of x is less than 0. So f prime of x is less than 0, or this graph of f prime of x is below the x-axis from negative 1 to positive 3. So we'll follow up again. Since f prime of x is less than 0 on the interval from -1 to 3, then f is decreasing on -1 to 3. So given the graph of f prime of x, it's not a very difficult problem if you understand the relationship between the derivative and whether or not the original function is increasing or decreasing. Okay, same type of problem. Below is the graph of f prime of x, so I'm going to label it f prime of x. Find the intervals where f of x, the original function, is increasing or decreasing. And again, we're assuming that these graphs go on forever. So the program I use to generate graphs doesn't ever include the little arrows. So what we're looking for is where the derivative is positive and where the derivative is negative. So over here, I'll take a look at where the derivative is greater than 0. So this graph is greater than 0 or positive from the x value -4 to the x value 0. So f prime of x is greater than 0 on -4 to 0 and past 2. So beyond 2 to infinity, from 2 to infinity, that's where my graph of the derivative is greater than 0. So f prime of x is greater than 0 in these intervals, so f is increasing on the intervals given. And then we want to find where f prime of x is less than 0, so where this derivative graph is below the x-axis, so that happens from -infinity to -4, this graph is below. So -infinity to -4, and from 0 to 2. This graph is below the x-axis. So f prime of x is less than 0 on this interval, so f is decreasing on the given intervals. So while there's no one necessarily perfectly correct way to write it, you do have to include certain components. So I need to see that you know that the derivative is less than 0. You can also write in words negative. So f prime of x is negative on these intervals. So f, so you can't, here's where you can't write that word it. So you can't say, so it is decreasing. What is it? You have to be very specific. So because f prime is less than 0 on these intervals, then f is decreasing on the given interval. So there's a lot of variations, little variations of ways that you can write it, but the core that needs to be there include the reasoning, because the derivative is less than 0 on particular intervals, f is decreasing on the interval. So you can either rewrite the interval or state on the given intervals, but those components need to be there to get the correct justification on the problem. All right, and in this last example, we again have the derivative graph given, and we're asked to find where f is increasing or decreasing. So f prime is greater than 0, so this derivative graph is above the x-axis. Now this one's slightly tricky. We can see there's a 0 happening at -2. So f prime of x is greater than 0 from -infinity to -2. But we have to remove -2 because that's where the derivative equals 0. So -infinity to -2, -2 to 1, because the graph's still above the x-axis from -2 to 1, and from 3 to infinity. So there can be multiple intervals as part of the answer. So f prime of x is greater than 0 on these intervals, so f is increasing on the above intervals. And then we'll go ahead and figure out where f prime of x is negative, or where this graph is below the x-axis. That's occurring from 1 to 3. So f prime of x is less than 0 on the interval from 1 to 3. So f is decreasing on 1 to 3.